Thanks everyone. Today I'm going to talk about learning embeddings for real world, leveraging internet search engine and spatial location relationships. It's a collaboration with Shujuan and Chen, all from China Mobile Research Institute. I have divided my talk into these four parts. Word embeddings is a figure engineering technique in which each word is represented as a numeric vector. The word embeddings allow to NLP tasks can be achieved. As in shown in this picture, word embeddings are learned based on the co-occurrence statistics of words in the corpus. However, word embedding techniques depend heavily on the frequencies of words in the corpus and are negatively impacted by failure in providing reliable representations for low-frequency words or unseen words during training. As words in a corpus follow a Ziff distribution, only a small proportion of total tokens are frequent words, while most of them are rare words. Therefore, how to learn qualified embeddings for rare words is a big challenge. From the human perspective, when encoding a new word, it's an instinct to take a look at its structure or look up its definition in a dictionary. Based on both ideas, some proposed techniques have attempted to employ subword information or lexical resources to predict the real-world representation. Subword-based approaches decompose each word into a bag of subwords and represent the real words by their subword embeddings. But the semantic meanings of subwords are not as explicit as that of the words, and is inefficient if the subwords of the real words are not seen during training. Knowledge-based approach induce the embedding using some lexical knowledge bases. However, if a real word is uncovered by the lexicon, the real word embedding will not be available. Now let me introduce our algorithm in detail. As the largest source of information in the world, the Internet consists of billions of pages or data in all fields. To figure out the meaning of real words, almost everyone's first priority has changed to retrieve it on the Internet and extract the useful information from the associated web pages. Inspired by this, we propose a two-step algorithm to learn real-world embeddings using the internet search engine and the spatial location relationships. Our algorithm consists of a code-tuning process and a fine-tuning process. The code-tuning process is to obtain the semantically related words for real words and to predict its approximate location in the vector space. The fine-tuning process is to adjust the co-screen vector of the real words intensively to optimize its meaning representation accuracy. And the final learned vector is the fine-grained representation. In the code-tuning process, we first find the relevant word to a real word from the web pages returned by the internet search engine, and compute the initial embeddings of the real word by averaging the vectors of these actuated words. The specific procedure of the code-tuning is described in this pseudocode. To measure the relevance score between two words, we take the co-occurrence information and the number of word meanings into account. The occurrence frequency is defined by the number of titles that contain the related words. The relevance score is proportional to the co-occurrence frequency and inversely proportional to the number of word meanings. Finally, we average the vector of the related words as the initial vector of the real words. According to the order of the top n relevant words, we further iteratively find the location of the right word in the vector space to make it to satisfy the constraints of spatial location relationships. The constraints are that if a word is more relevant to a word than other words, the distance between the right words and this word is closer than the distance between the right words to others in the vector space. As the semantic words have been ranked by the relevance to the right words, the semantic relatedness between the right words and a higher ranking word in the semantically related word set is higher than that between the right words and a low ranking word. And the semantic relativeness between two words can be represented as the cosine distance of their vectors in the vector space. Therefore, the constraint can be expressed as the second formula. Then the vector of the right words is iteratively flattened as the third formula. Now we present our experimental settings and results. We use word similarity as the evaluation framework to verify the reliability of our algorithm. The Spearman correlation is computed for measuring the accuracy of word similarity tasks. The percentage of missed pairs is adopted to evaluate the coverage ability of our approach. A snapshot of English Wikimedia is used as the training corpus. We use 4 different benchmark datasets to perform evaluation, including 2 general domain datasets and 2 biomedical datasets. We first take the task of word similarity computation to investigate the influences of the two hyperparameters in the costioning process for the quality of the learning right words embeddings, including the number of relevant records and the number of semantically related words. And seek the optimal range of the two parameters. From the results, we can see the Spearman correlations of our algorithm on the full path all increase at the early stage and then decrease with the two parameters generally. Second, based on the above results, is maybe more appropriate to set the parameter m and the parameter n to 105 respectively. In this way, we can learn better real-world embeddings. We compare the Spearman correlations of the learned cross-grained embeddings with that of the fine-grained embeddings to verify the effectiveness of the fine-tuning operation. To have a fair comparison, we report the performance of the learned real-world embeddings on the multiple datasets in 4 different dimensions. From the results, we can see that the Spearman correlations of the fine-grained embeddings outperform that of the coarse-grained embeddings on the 4 datasets. It demonstrates that the quality of the coarse-grained embeddings can be further enhanced by the fine-tuning process. In this experiment, we compare algorithm with the word vector algorithm and the 6 English real-world embedding learning algorithms. From the results, we can see that whether for domain general rare terms or domain-specific rare terms, nearly all the vectors can be learned by our algorithm. With respect to the quality of the real-world representations, our algorithm also outperforms the other approaches on the 4 benchmark datasets. To investigate the scalability of our approach on multilingual words, we evaluate our algorithm on Chinese rare words as well. We use 2 Chinese benchmark datasets to perform evaluation including the word theme 240 and the word theme 296. We compare our algorithm as the word vector algorithm and full Chinese real-world learning algorithms. From the results, we can see that our algorithm can get better coverage abilities and representation qualities for the real world than the other approaches. To summarize, we have presented a novel algorithm to learn embeddings for real words, which consists of a code-sending process and a fine-tuning process. Second, our algorithm has better coverage ability for real words than the other approaches. Third, our algorithm also performs better in the quality of embeddings for real words than the other approaches. Thank you very much for listening to me. If you are interested, you can contact me with this email. Thanks a lot.